Hello, this is the second session about quadcopters. I hope you found the first session useful. In this session, I'm going to discuss quadcopter sensors, and I will focus on the gyro sensor. The quadcopter sensors are gyro, accelerometer, compass, barometer, sonar, GPS, and some other sensors such as optical flow. Gyro is a mandatory sensor. Without gyro, we cannot fly quadcopter. It is used for balancing. Accelerometer is used for self-leveling. Compass is used for orientation, the yaw orientation, and it enables us to fly in modes such as the head-free flying. Barometer and sonar are both used for altitude hold. Barometer is used to measure high altitudes. This is an advantage. It can measure altitudes up to several kilometers. For sonar, you can only measure a few meters, typically up to 5 meters. However, sonar is much more accurate than barometer, giving that you are flying on solid ground, because if the ground is soft, the ultrasonic waves will not be able to reflect from ground to the sonar, and it will not be able to detect the height accurately. Parameters, on the other side, depends on the environment and the temperature, so you need to calibrate your parameters whenever temperature changes. Actually, barometer have a built-in temperature sensor that is used together with the pressure sensor to calculate the altitude. GPS is used for return to launch and UAV flying. Now let's focus on the gyro sensor. Typically, gyro is a mechanical system that is used for measuring and maintaining orientation based on an angular momentum. It consists of a rotor that spins very fast around a spin axis. There is gimbal here, and there is a gyroscope frame. When rotor spins very fast, if you hold this gyroscope frame and move it like that, you will find that the rotor will stay horizontal. It will not move with you. And this is the main idea of gyro. However, on quadcopters, we cannot mount such mechanical system, and we need to use another technology, which is totally electrical systems. Gyros on quadcopter boards, on quadcopter flying boards, are found as ICs like that and ICs like that. This is the famous IMU 6050, and this is a gyro you can find this is a single axis gyro. You can find it on some boards, such as the KK2, sorry, the KK version 2.1. It's not the KK2, it's KK version 2.1. These gyros are made because of the technology called MEMS. MEMS is Micro Electrical Mechanical System. It enables us to build mechanical systems inside ICs. This is one of the outcomes of the nanotechnology. Okay, let's go back to gyros and its role in quadcopter. Gyro in quadcopter measure angular velocity. In another way, it measures how fast or the speed of which your quadcopter rotates in pitch, roll, or yaw. The measuring unit is degree per second. So it's like the RPM, because it wants to measure how fast your quadcopter rotates in order to reverse this action by controlling motors, and that's how it keeps your quadcopter balanced. Gyros can measure the angular velocity in different ranges. you can use ranges such as 250 plus or minus 250, which is clockwise and counterclockwise. And you can use gyros that can measure fast rotations such up to 2000 degree per second. And here I am talking about gyros that is available for our commercial boards. Maybe I'm sure there are a lot of gyros that are much more sensitive. Typically, you can fly your quadcopter using the 500 range. A question here is, why not we all use the 2000? The answer is, when you use a high range, you lose accuracy, because normally the output is sometimes 10, 12, 16 bits. So if you dedicate the 12 bits for 500, you will be able to detect small movement, and then you can respond to even very small movement in the quadcopter, and your quadcopter will be more stable. On the other side, if your quadcopter moves aggressively, the output of gyro will saturate, and you will not be able to calculate the actual angular velocity of your quadcopter. So here you might need to use the 2000 scale. So it depends on your application, but typically 500 can fly your quadcopter very well. Also, there are two types of gyros that we can find on our quadcopter boards. There is a digital gyro and analog gyro. Analog gyro, using analog gyro, the output of the analog gyro is just a voltage in a single pin. For example, if you, let's take the x-axis gyro and we want to measure it, we will use, let's assume an IC with 3 pins. The first pin is for x-axis, the second pin for y, the third pin for z-axis. Then we will measure the voltage of the first pin, which is the x-axis, which should range from 0 to 3 volt, and we divide it from minus 500 to positive 500. We will measure it using the analog ports of our microcontroller, and that means that any noise on the board, any voltage noise on the board will affect our measure accuracy. Digital gyro, on the other side, use the I2C communication. I2C communication enables the microcontroller to send commands to the gyro, and you can even change the range of the gyro programmatically from 2000, 50, 500, etc. Because using I2C, you can send a command to the gyro and order it to change its range, and even implement inner filters to remove noise. I mean by noise here, noise that exists from vibration of the quadcopter. Here is the IMU 6050, and this single IC contains 6 sensors. 3 of them are gyros, and the other 3 are accelerometers. Here we can find an old board, which is the KK version 2.1, which contains 3 separate gyros, one in x-axis, y-axis, and z-axis. We should notice here something important, that gyros have directions. You cannot just mount the IC, the gyro IC, on your board except in you need to put it in certain directions, which is the x-axis, y-axis, and z-axis. Here we can see an example that the z-axis is mounted vertically on the quadcopter board. For modern gyros, there are some signs here that help us to mount the board correctly in the quadcopter, and that's why we put the board in the plus configuration of the quadcopter. We put it in a way different than the X configuration. In the X configuration, we need to rotate the board by 45 degrees. However, in my HefnyCopter firmware, I made this calculation inside the firmware, so you don't need to physically rotate the quadcopter board. Anyway, now let's go to quadcopter itself and how gyro measure the movement of quadcopter. Here we have two positions of quadcopters. The first one is quadcopter that is hovering, and it is totally vertical. And there is other quadcopter that is tilt, but it's not rotating like that. It's not rotating, it's just tilt, and it is moving to the left direction. And in both positions, for gyro, it reads 0. For gyro, these two positions are identical and they are perfectly stable from the viewpoint of gyro because there is no rotation. So the angular velocity is 0 in both positions. If the quadcopter starts to move in this direction clockwise, then the gyro will start to read data. But unless it moves, the gyro will read 0. Now let's go back to our first session just to review some rules that we will use to calculate gyro in the next slide. The flying rules that we discussed in our first session is that the thrust is equal to motor 1 thrust is equal to motor 2 thrust is equal to motor 3 thrust and equal to motor 4 thrust, and is determined by the thrust stick, and it is used to we increase it and decrease it to move the quadcopter up and down. If we want to make motion in roll or pitch, for example, let's take roll, we increase this thrust and we decrease this thrust, but by delta. So if we increase M2, motor 2, by delta to be M2 plus delta, we need to decrease the same amount from motor 4. Why? Because these motors rotate, for example, counterclockwise, and these motors rotate clockwise. So we need to maintain the torque in this axis equal, regardless of changing the thrust for roll. So if we want to roll, we need to maintain the torque equal in this axis, otherwise it will yaw. If we want to yaw, we need to decrease thrust of these motors and increase the thrust of these motors, or vice versa, to roll either clockwise or counterclockwise. Now let's go to our final slide and most important slide, how we can use gyro to stabilize our quadcopter. This is a simple firmware. Almost any firmware for quadcopter consists of these steps. We can complicate the firmware, add more sensors, complicate the calculation of calculating the angle of quadcopters. However, this is the base steps that all firmware should comply in order to fly a quadcopter. First, we read stick positions from our receiver. Then we read sensors. In the simplest port, we read gyro values. Then we adjust our motors. First, we initialize the motors with the RX throttle. So this is the first rule. Then we add ailerons and elevator sticks values to make the pitch and roll motion. Then we add rudder sticks for motors, motor 1, 2, 3, 4. Here this sign should be positive, and this should be negative and negative. There is a mistake here. We add rudder in order to generate the yaw movement. Now let's go to the gyro part. In the simplest way of implementing gyro in quadcopter, we can just read the gyro value and multiply it by a constant and use this value to control the motor. And this is the delta that we talked about in our first session. So imagine our quadcopter. Let's go back to this slide. Imagine our quadcopters move, it tries to rotate like that counterclockwise to get in this position. This motor the gyro will read an angular velocity in this direction. It is a velocity, so it will read an angular velocity in this direction as long as this quadcopter rotates. Based on the previous formula, we can take the value that reads and multiply it by a constant, either to increase or decrease it based on our scale, and then we can decrease the thrust of this motor and increase the thrust of this motor by the same delta in order to prevent it from moving or from rotating counterclockwise and keep the quadcopter stable. This is the whole idea. And this is what we call the P factor, or the P is a parameter in the PID system. So the simplest way to build a quadcopter firmware is to use gyros only and to just simply multiply it by P and just add it to the motor outputs using the rules that we discussed here in our flying room. Then, after we calculate the motor outputs, we just send the output to speed controllers. Speed controllers accept signals from, typically from 1 millimeter, from 1 millisecond width to 2 millisecond width. 1 millisecond means idle, 2 milliseconds means full throttle. I hope you enjoyed and you find this session useful. Please write your comments in YouTube, and I hope third session will be soon. It will be about accelerometers and how we use it to combine it with gyro to calculate the angles. Thank you.